Hello everyone, welcome to today's presentation. I'm excited to talk about applications of trigonometry. On this first slide, you'll see the title of our session. We'll explore how trigonometry is used in various fields and real-world situations. Over the next few slides, we'll cover key concepts and practical examples. Let's get started and discover the fascinating ways trigonometry impacts our daily lives. Let's take a closer look at the contents section of our presentation. Here, we see that the second item is applications of trigonometric ratios. This is a crucial part of understanding how trigonometry is used in real-world situations. We'll explore various practical examples where these ratios come into play, such as navigation, architecture, and even astronomy. Recognizing these applications helps us see the relevance and importance of trigonometry beyond the classroom. By the end of this section, you'll understand how these ratios are powerful tools for solving everyday problems involving heights, distances, and angles. This ties into the overall theme of the presentation, which is about making trigonometry both understandable and applicable. Let's talk about what trigonometry actually is. Trigonometry is a branch of mathematics that focuses on studying triangles. Specifically, it looks at the relationships between the sides of a triangle and the angles between those sides. These relationships are fundamental because they help us understand and solve problems involving angles and distances. Throughout this presentation, we'll see how trigonometry connects to real-world applications and why it's such an important tool in various fields. So, in essence, trigonometry helps us analyze the geometry of triangles and unlocks the secrets of angles and lengths. Now, let's explore the exciting applications of trigonometric ratios. These ratios are incredibly useful tools in real-world situations. For example, we can use them to find the height of a tree or a tower without directly measuring it. Imagine standing some distance away and knowing the angle of elevation. With that, we can calculate how tall the object is. Similarly, we can determine the height of a water tank or even measure the width of a river. Another practical application is figuring out the distance of a ship from a lighthouse, which is essential for navigation. These examples highlight how trigonometric ratios help us solve problems involving heights and distances that are otherwise difficult to measure directly. So the key point here is that trigonometry isn't just about abstract numbers. It's a powerful tool that applies to many everyday and technical situations, connecting theory to real life. This understanding will help us see the relevance of what we're learning and how it can be used beyond the classroom. Now, let's look at something quite simple, but really important in understanding how we see objects: the line of sight. When children see an airplane flying overhead, what do they naturally do? Exactly, they tend to look up. And what we observe is that the straight line connecting their eyes to the airplane at that moment is called the line of sight. This concept is key because it helps us understand how we visually connect with objects in our environment. By understanding the line of sight, we can better grasp how we perceive objects at different angles and distances, which ties into the overall theme of visual perception and understanding spatial relationships. So essentially, the line of sight is just a straight path our eyes follow to focus on something we're looking at, like that airplane soaring above. Let's talk about the angle of elevation. This is an important concept when we observe objects like airplanes from the ground. The angle of elevation is the angle that the line of sight makes with a horizontal line drawn from your eyes. In simpler terms, if you look up at an airplane, the angle between your horizontal line of sight and the actual line of sight to the plane is called the angle of elevation. It helps us understand how high the object appears relative to our eye level. This concept is crucial in fields like navigation, astronomy, and even in designing radar systems. By understanding this angle, we can make accurate measurements of the height or distance of objects that are above us. So, the angle of elevation essentially connects our perspective with the actual position of objects in the sky or at a distance. Let's take a closer look, the angle of elevation diagram. This diagram is a visual tool that helps us understand how we measure angles when looking up at an object from a certain point. The key idea here is that the angle of elevation is the angle between the horizontal line from our eye level and the line of sight to the top of the object. Notice how the diagram highlights that this angle is always measured from the observer's eye level, not from the ground. This concept is crucial because it allows us to set up right triangles, which are the foundation for calculating distances and heights using trigonometry. By understanding this diagram, we can see how to apply trigonometric ratios, like sine, cosine, and tangent, to solve real-world problems involving heights and distances. It connects directly to our overall theme of applying math to practical situations, showing how geometric principles help us analyze and interpret the world around us. Now, let's talk about the angle of depression. Imagine you're in an airplane and you look down at some object on the ground. The angle of depression is the angle between your line of sight, so the direction you're looking, and the horizontal line that extends straight out from your eyes. This is an important concept because it helps us understand how we observe objects from a height. The key point here is that the angle is measured downward from the horizontal, not upward. Recognizing this angle is crucial in navigation and surveying, as it allows us to determine distances and heights indirectly. So, in the bigger picture of our presentation, understanding the angle of depression helps us grasp how angles are used practically in real-world scenarios like aviation and mapping. Let's take a closer look at the angle of depression diagram. Here, you can see how the angle of depression is measured from the horizontal line downward to the line of sight toward an object. This angle is crucial because it helps us determine the position of an object relative to a point of observation. Notice that the observer's eye level creates the horizontal baseline, and the line of sight extends from the observer to the object. The angle between these two lines is what we call the angle of depression. Understanding this concept is essential when we're analyzing situations like viewing a ship from a cliff or calculating the height of a building. It connects directly to our overall theme of using angles in real-world measurements. So, grasping how the angle of depression works allows us to solve many practical problems involving distance and height estimation. Let's dive into the topic of trigonometric ratios. These ratios are fundamental in understanding the relationships between the angles and sides of right-angled triangles. They help us solve for unknown angles or side lengths when some information is given. The key ratios we focus on are sine, cosine, and tangent. Sine of an angle is the ratio of the length of the opposite side to the hypotenuse. Cosine is the ratio of the adjacent side to the hypotenuse. And tangent is the ratio of the opposite side to the adjacent side. These ratios are crucial because they allow us to analyze and solve problems involving angles and distances, which is a core theme in our overall exploration of geometry and trigonometry. Understanding these ratios sets the foundation for more complex concepts and real-world applications later on. Now let's look at solving a problem related to height and distance, specifically the height of a tower. Imagine you're standing at a point on the ground, which is 30 meters away from the foot of the tower. From this point, the angle of elevation to the top of the tower is 30 degrees. Here, we denote the foot of the tower as point B, the top as point A, and our observation point as point C. So, in triangle ABC, we know the angle of elevation at C is 30 degrees, and the horizontal distance from C to B is 30 meters. The key concept here is that this forms a right-angled triangle, where we can use trigonometry to find the height of the tower. Since we know the angle of elevation and the horizontal distance, we can apply the tangent function, which relates the opposite side, that is, the height of the tower, to the adjacent side, the distance from the point to the foot of the tower. By setting up the tangent of 30 degrees as the ratio of the height of the tower to the 30 meters distance, we can solve for the height. This is a classic example of how understanding the relationships in right triangles helps us solve real-world problems involving height and distance. So, in summary, this problem illustrates how angles of elevation and basic trigonometry are powerful tools for determining heights that are otherwise difficult to measure directly. Let's look at problem 2, which deals with the height of a pole. Imagine a circus artist climbing a rope that's 20 meters long, stretched tightly from the top of the pole to the ground. Our goal is to find out how tall that pole is. Now, from the figure, we observe that OB represents the pole. In triangle ABC, the key angles and lengths are important. The rope makes a 30-degree angle with the ground, which is a critical piece of information because it allows us to use trigonometry to solve the problem. Since we know the length of the rope and the angle it makes with the ground, we can apply the sine function, which relates the opposite side, that's the height of the pole, to the hypotenuse, which is the length of the rope. So, by setting up the equation, we find that the height of the pole is 10 meters. This example highlights how understanding the relationships within right triangles and applying basic trigonometry can help us solve real-world problems, especially in contexts like construction or engineering, where knowing precise measurements is essential. All right, let's look at problem 3, which is about the length of the string. Imagine a kite flying high above the ground at a height of 60 meters. Now, this string is tied to a point on the ground, but at some point, it's also inclined at an angle. Specifically, the string makes a 60-degree angle with the ground. Our goal here is to find out how long that string actually is. To visualize this, let's consider the triangle formed by the kite, the point on the ground where the string is tied, and the point directly beneath the kite on the ground. This forms a right triangle, which we call deltaculp. In this scenario, K represents the kite, and P is the point on the ground where the string is tied. We need to find the length of the string, which is the hypotenuse of this triangle. Remember, the key concept here is using trigonometry, particularly the relationship between the angle, the height, and the length of the string. Since we know the height of the kite and the angle of inclination, we can use the cosine function to find the length of the string. So the main point is, by applying the right triangle relationships, we can calculate the length of the string accurately. This ties back to our overall theme of understanding how geometry helps us solve real-world problems, like this one involving the kite and its string. All right, let's look at this problem involving a tree that's been broken by a storm. Imagine a tall tree, which we'll call AC, and due to the storm, it breaks somewhere along its height. Now, the broken part bends over, touching the ground, and forms an angle of 30 degrees with the ground. The key here is that the top of the tree, after breaking, touches the ground at a point that's 8 meters away from the base of the tree. So, if we think about it, the broken part of the tree creates a sort of leaning segment, like a triangle with the ground, the tree's original height, and the bent part. Now, the main goal is to find the original height of the tree, which is the sum of the height before it broke, and the height of the broken part that remains attached. In the diagram, we see the broken part forming a 30-degree angle with the ground, and the horizontal distance from the foot of the tree to the point where the top touches the ground is 8 meters. This setup involves some basic trigonometry, specifically the sine and cosine functions, to relate the angles and sides. Remember, the original height is composed of two parts, the part still standing and the broken, bent part. By analyzing the angles and the distances involved, we can use these relationships to find the total height of the tree before it broke. So, as we work through this problem, keep in mind how the broken part and the ground form a right triangle, and how the given angle and distance help us determine the lengths of the segments involved. This is a great example of applying trigonometry to real-world problems, connecting the geometric concepts to tangible situations like a fallen tree. Now, let's look at problem 5, which involves complementary angles and tower height. Imagine a tower, which we'll call AQ, and 2 points, R and S, positioned at 4 meters and 9 meters from the base of the tower, respectively. Both points are aligned straight with the tower, meaning they're on the same line. The key detail here is that the angles of elevation from these points to the top of the tower are complementary, meaning their sum is 90 degrees. So, if we let one angle be theta, then the other must be 90 minus theta. This relationship is crucial because it allows us to connect the two angles mathematically. Next, we examine two triangles, delta-ACR and delta-AX. By analyzing these triangles, we derive equations based on tangent ratios, since tangent relates the opposite side. Here, the height of the tower to the adjacent side, which is the distance from the point to the tower's base. By multiplying the equations obtained from these two triangles, interestingly, we find that the height of the tower simplifies to 6 meters. This problem beautifully illustrates how understanding the properties of complementary angles can help us solve real-world measurement challenges, and it highlights the power of geometric relationships in deriving unknown heights. Connecting these concepts to the overall theme, it shows how angle relationships and triangle similarity are fundamental tools in practical geometry.